at the first 2 pairs that it almost doubled the number, while at the end for the last compound, it remains almost the same. It is a bit smaller, but it's almost the same. Photophysical properties for these compounds are important because they could be used also as biomarkers. Okay. And conclusions. We successfully synthesized the 3 ligands and their lutetium-parathymine complexes. We confirmed their structures using proton NMR and ER spectroscopy, and then we evaluated their photophysical properties. Future research will investigate their potential application as anti-cancer drugs. And I would like to express my gratitude for Association of Hungarian Chemists for the financial support. And of course, thank you for your attention. So much, Andrea, for your time. And now I will open the floor one last time for questions. Yes, yes, these are novel compounds. They do not exist in literature yet. I don't think it will be a pill. I think that it will be something which is locally applied on, but I don't really know because we do not study this part. But they say that curcuminoids are good because they can be applied locally, so you don't have to take a pill and to have the side effects all over your body. It's only locally applied. And for the first question, I'm sorry, other NSAIDs were already tested. For example, I think that there's literature for curcuminoids and aspirin complexation, but we tried new ones. Thank you for your question. The literature says that it's non-toxic, but I don't know exactly the metabolites for the compounds because, as I said, there are new compounds, so they have to be studied. Thank you for your question. Thank you.
Congratulations, Andrea, again. And as we come to the end of this presentation session, I will invite you to enjoy the next coffee break. Use this time to get some fresh air and, of course, to network. And we are looking forward to seeing you here at 20 minutes to 15 for the RKS company presentation.
Welcome back. We are continuing with the final session of this segment. Please welcome Aline Forakash and Silviana Bretoiu from Arches with a company presentation. Alin Forcaș is a Romanian engineer and the CEO of Arches. He has a strong technical background and focuses on industrial engineering and software solutions. Arches provides specialized engineering and IT services, working with international clients and emphasizing quality and long-term partnership.
Thank you very much. That was our presentation as a company. I'd like to introduce Silvana Bretoiu, my colleague. She's application engineer in one of our teams and graduate from chemical engineering, this faculty. So it at the initial time of planning, I have to keep it here, right? Okay. Um, okay. Just a second. Maybe not. Yes. I'm gonna keep it here. At the initial time of planning of the meeting, I wasn't sure if Silvana would be able to join me, but actually I'm quite glad for two reasons. Um, in about 15 minutes, I'm gonna have to step out because I need to get into a last minute schedule call. On one hand, on the other hand, Silvana is actually better suited to talk a bit about some of the technologies she's working with, which I think might be of quite an interest to you here at this faculty. So, trying to to keep the timeline, I'm going to go through our slides. Um, yeah, obviously we are located here in Cluj. We all know this is our usual presentation that we are giving in front of our customers. Um, we've been favored in the last 15 years because we've been here for 15 years. We've been favored by the development, the strong development in the services and software development segment here in Cluj. So we've been here for 15 years, and I think it's still the place to continue to evolve. Now, in our history, we are a services provider in customer support, engineering, and software development. And in bold, you can see the the devices, the industrial equipment with which we are working on daily basis. We started in 2011 with industrial valves and went on developing our knowledge and skills in actuators and then in automation in safety systems. And somewhere around 2016, 2017, we kind of attach the software development part because we saw the need at our clients that we always have to bring something additional besides the engineering knowledge in order to be able to deliver our services. So this is the reason why we started a bit late. According to the timeline, we started in the software development field as well, but we have a specific differentiator in that area as well. Now, I think what's of particular interest is that in October 2019, we actually started developing our services in analytical industry, where we typically look for chemical background, and we do have a lot of chemical engineers in our company. A lot with respect to the size of our company, basically. Um, these are some of our customers. You may know or may not, but these are enterprise customers, so companies which are typically in the area of hundreds of millions of euros annual sales. Krone is doing valve flow meters. Pentair, Tyco, Bifi are working in the valves actuators. Servomex, about the one of our clients, which about which Silvana will say few words. It's actually in the analytical instrumentation. This is who we are actually as a company in one slide. So with respect to maybe other companies which are acting globally, we are a small size company, purely engineers inside. So from mechanical all the way to chemical engineering, automation, and software development. But we are acting globally, meaning that through our services, we actually get in contact with the latest projects and the latest products that are being commercialized or deployed in Europe or worldwide. In 2021, we had our 10 years anniversary, and you can see a couple of shots, photos from that event, which was an important milestone. We actually also refine our mission and vision. And occasionally, if you encounter the previous logo, that's actually in 2021, we decided to change it to the new one and adding the, uh, the, the brand attribute, how they call it, quality engineering and software. And Silvana, now to you. I'm gonna let Silvana talk a bit about Servomex because Servomex is one of our clients with manufacturing gas analyzers, and Silvana, chemical engineer, works daily with these devices.
Hi, as Aline mentioned, I am a chemical engineer. I finished this same university. I remember sitting in these desks and nice memories. I finished 6 years ago EPCP program and then ECAP for master. Since 2020, I started working for Arcus and also for Servomex. At the beginning, I was sales engineer. We helped with the quotation, the order, deliveries, everything that was needed. And then I moved to a position of application inquiries, which is more focused on the engineering, the chemical engineering part. Servomex, it's a company, it's part of Spectris and has a history of over 50 years of experience in gas analysis. It has many technologies, many products that were developed over time. And important would be the ones you see, Air Products, Air Liquide, Linde, Samsung. We activate a lot in the semiconductor industry for the purity side, and also on the industry and the petrochemical and other region where gas analysis is needed. The technology that we use, quite a few. I'm gonna go a bit fast among them, explaining, but not in such details. And what I want to emphasize is a few stories of what we actually do and what a day in our life looks like. For me, as an application engineer, the day starts with different inquiries from customers. They are coming to us asking, sending us the process data and asking what we can offer them if they want to measure different gases. So based on what they want to measure, the industry that they activate in, we offer solutions. The domain or the technologies that I'm more confident or I know better are my strong suit would be the gas chromatograph, which I'm not sure if you study gas chromatograph. I know you have some liquid chromatograph here, but for a gas chromatograph analyzer called Chroma for short, we measure impurities measure ppm or ppb levels of different gases for purity. For example, if you know the customer Linde, they provide oxygen for hospitals, and that oxygen needs to have a certain purity. We can provide the analyzer that will guarantee, or they will measure the impurities, so the oxygen is qualified to be sent to hospitals. The request usually comes as we want to measure these impurities in oxygen or in nitrogen or in any background gas. We at the code stage are offering a solution, looking at the columns that need to be fitted, the technologies that need to be implemented in the analyzer. Then we have the order, they place the order, and we move to building the analyzer. From the order stage, an application engineer also needs to approve, to look again, to see everything is all right according to the specification, and then it can go into production. It's built, and then we check again to make sure that everything works properly. The results that the analyzer has are okay, within the limits, and we can send them to the customer. Then it's released and can be, of course, delivered, and it works. It can be put in functions. Another technology to say that we have and it's used worldwide would be paramagnetic. They are measuring oxygen. It's used in various applications, and usually we have the same data sheet where we have the data, the temperature, the components, and we are looking to see the material compatibility of everything. We know every part of the analyzer, and we need to check if what the stream has is compatible with our components. For example, we had an application where one of the components would be hydrogen chloride. Usually we don't like that combined with stainless steel if there is water present. But if we can remove all water, stainless steel is fine. So we put this condition: if you can remove all the water, the analyzer will be fine, will work, there's no issue with stainless steel. Of course, the customer guaranteed that they can remove the water, no problem. They also came back a few weeks later. Are you sure that it's gonna work? We assured them that yes, if they remove the water, there will be no problem. But of course, they came back third time asking the same question: are we sure that it's compatible? And we need to look and provide evidence with the data there are different tables that assure the material compatibility. So we need to provide evidence to ease the customer mind that everything will be all right and the analyzer will work. And if they have any concerns, there are no issues, we can offer also special materials. But they need to let us know what the preference are or what they want and would like from us. Similar to this one, we had Zirconia application where we have an analyzer called 2700. We usually use it for carbon capture or for furnaces. We are measuring oxygen and the combustibles to make sure that the combustion was complete and there is no loss of fuel or any other materials that the customer doesn't want. We, of course, ask for the process data. They are telling us, yes, it's combustion, it's easy, it's nitrogen, oxygen, you have no issues. Then they send us a picture of the furnace. The furnace has rust all over it. And of course, we are raising the question, are you sure you don't have anything else in the stream that might corrode? Because if we are using stainless steel as a probe, there will be issues. No, everything is okay. Please double check. And they, of course, came back. It was corrosive. We need to use another different material. So basically, you need to have a lot of patience in these cases and to have attention to details. It's very important if you have something that you are not very sure about, and just don't make assumptions. You need to be sure, you need to be calm, you need to ask questions. There is no issue in asking questions, and you need to feel confident about what you are saying, about what are you proposing. Yeah, this is pretty much what our day looks like. It's complicated, but it's fun. If you have any questions for us, if you want to know something that we can, sure. Analyzers. Yes. Yeah, the factory is in UK based. That's the factory, and that's where they are built. Yeah, it's worldwide, so we are working every continent. We don't really adapt technologies. We fit a technology that we have, and it's developed to their needs. Mm. um, I'm not really sure what the most challenging is, because we've been through so many challenges and overcome each one of them. At some point, that was the hardest challenge, but then we moved to another. So it, one of them was that example that I gave with the hydrogen chloride, that I started to doubt myself that what I was finding and in literature was true. But yeah, you double check with other people with experience, and you ask questions if you don't know. So basically, it's all about communication. It's nothing that cannot be resolved. You can search and find an answer.
We've been supporting the conference for many years. I think you've picked a good field to learn and to grow in the future. And it's I'm an automation engineer, I'm not a chemical engineer. I have an automation background, but maybe due to my history going back in working in this type of services delivery, for which I'm working for 20 years now, I can see how important is the technical background when you're actually reviewing an application for a customer, which at the beginning looks like, okay, someone wants to buy a gas analyzer. This looks like a transaction, a sales transaction, and um, it's gonna go like in an online shop and select, okay, I'm gonna get this, and then 3 days later or 3 months later, they get a box. And actually, it doesn't work like that, because before getting to what needs to be manufactured, it's an entire discussion and process in which technical details, and after that commercial details, and after that geopolitical details like compliance, they have to be clarified before you can actually place an order for a gas analyzer. And it may seem at first a sales and administrative process, but actually everyone talking with everyone in along the way in the chain of discussion has a certain technical understanding of what is being asked and what they are expecting. So um, it's not going to go away, chemical engineering. So um, keep studying. Thank you very much and success.
Okay, thank you very much. Are there any questions? Thank you very much for being here. Next up, we welcome two participants for the chemical engineering section. First up, we invite Narcis Madalin Arsene with hexanitrometalates, structural and thermal analysis.
Nu știu dacă pot de pe telefon. Mai bine. Ai laptopul la tine? Ba nu, stai așa. Da, nu știu pe mine. Am trimis, bine, dar nu contează că... Da, da, da. Eu ăla de experiență. Între timp o trimis și pe WhatsApp. Încercați să sună mai întâi. Da. Da, ora. Da, da. Nu știu pe mine. Nu, asta e când am întrebat și... Nici o problemă, că deci să înțeleg, am un timp extra. Da. Da. Am timp extra. E destul de ce. Sau era pe ceva de O să încerc să vă trimiți. O am, dar nu am stipulat, nu m-am gândit că... Adică aș putea să prezinte urmă persoana după mine și eu să prezint. Păi eu vă trimit prezentarea pe WhatsApp, de conectăm în tabla de date de și îl downloadați direct în calculator. E corect, atunci și... Madalin. Mai putem spune numai? 0751 04 Este asta funcționează? Da. Ok, nu înțeleg. Deci tot are să vorbesc. Deci că v-am plictit. Știi? De ce? N-aveți cumva downloadat? Da, eu vreau să zic pachetul cu fonduri, poate nu e downloadat. Încercați să-l deschideți din... Aveți Copilot, aveți...
Da, e instalat aici.
Da. La tine mergea? Ok. Așa că. Am zis.
Atunci poți să-mi salvezi, adică să-mi pui report.
Da. Da, niște.
Ce trafici? Uite. Uite, vreau să fac așa să
be focusing on structural and thermal analysis. A bit of an introduction. These inorganic coordination compounds have a complex anion made out of transition metal surrounded by 6 NO2 ligands in octahedral geometry. And the negative charge is compensated by various counterions which can differ from each other, as we will see. Because of this, they present a very low solubility in almost every solvent. And because of the charge transfer between the metal and the ligand, they have very intense colors, which makes them perfect for manufacturing pigments, such as aureolin, which is a pigment that is not in use today, although it's still produced, but is the final product of the identification reaction of the potassium ion. Furthermore, these complexes can be used as precursors for mixed oxides, such as the lanthanum and nickel perovskite, which is used in catalysis and manufacturing of nanomaterials such as nanotubes. Because of their simplicity, we can look at the coordination modes of the nitro ligand, and we will see that each and every one of them is present here. So we have the nitrito bonding, in which the ligand coordinates the metal through one of its oxygens, and the nitro bonding, in which the ligand coordinates through the nitrogen atom to the transitional metal. Why I'm saying why these are the first ones is because we'll be mainly focusing on these coordination modes because they can they are isomers and they can switch at temperatures. And we have the chelatic bonding, which chelatic mode, which can be possible, which is made possible by the resonance effect of the ligand. The bridging through the oxygen atoms, same with the chelatic one, and the bridging through the nitrogen and oxygen atoms. For the synthesis method, it's a very simple one and very efficient. We have two solutions. We used water as a solvent. And the first solution is a potassium nitrate solution in a tenfold excess. And the other one is a solution containing chlorides. Now, it can be just the chloride of the transition metal, or a mix of chloride salts, one with the transitional metal and the other containing a counter ion, which we wanted to implement in the compounds. The counter ions can be strontium, lanthanum, holmium, and europium. And these two solutions were mixed. They were added to each other, one dropwise to the other, stirred under constant stirring and at low temperatures in ice for 1 hour. The result is a very colorful solid, which precipitates almost immediately. But not all complexes are have the same stability. Oops. So, regarding stability, we can see that the potassium hexanitrocuprate didn't precipitate at all and didn't form. This is because of the strong distortions caused by the Jahn-Teller effect, which decreases the lattice energy and makes solvation favorable. So it did not form. But all the other complexes precipitated immediately and with good a good chunk of them were extracted. Okay. The problems that the hexanitrocuprate presented are gone because we implemented strontium in the mix. And strontium gives off stability through its charge of +2, which makes the polarization of the bond, increases the polarization of the bond and makes the bond stronger. The volume of strontium also helps because it decreases the distance between ions, and the result is a very stable, compacted structure that doesn't allow water in and makes it very hard to dissolve these compounds. So we and the last one, the lanthanide family. The ones containing lanthanides are the most stable because of the oxophilicity of the lanthanides. So we sorted them into three families. These families are sorted by counter ion, and these compounds were analyzed by various methods. The first one is infrared spectroscopy. Infrared spectroscopy was used to determine in which coordination mode the ligand is after the synthesis and if any clandestine molecules like water or any other ion infiltrated the complex. Later, infrared spectroscopy was done up to 300 degrees in order to accompany the thermogravimetry and differential scanning calorimetry that we did up to 1,000 degrees. Furthermore, the powder X-ray diffraction was done on the complexes, and we observed that those with two different counter ions were isostructural, of course, with small differences. And the single crystal X-ray diffraction, we managed to grow just one crystal, unfortunately, but the structure that was unraveled was used as a base for our DFT calculations in order to better understand the ER spectrum. Moving on to structural particularities of these complex, the one that I was talking about earlier. This is potassium hexanitronickel, and as you can see, it has a pesky water molecule there because I couldn't get rid of it. This is the crystallization molecule, and the asymmetric unit, as you can see here, is very simple, and we can see the two types of potassium ions. The most interesting one is the potassium noted K2 because it is coordinated with the oxygen of the water molecule. So the water molecule acts as a bridge between two potassium ions. If we grow this fragment, we will have that result, and that result shows us the first coordination sphere. We can clearly see the octahedral geometry, and the second coordination sphere, which shows us the potassium ions, and you can see the water being a bridge. For the experimental values, the lattice parameters, we have the crystal system. It's a trigonal crystal system, and the values of the A, B, and C lattice parameters coincide with old studies that were done on this complex, which further assures us that this is the real formula. Okay, here you can see the unit cell of the complex, which has three formula units, and a clear representation of the geometry is found in this complex, like the octahedral geometry for the transitional metal, and the potassium ion, which is coordinated with 9 oxygen atoms, forming a three-capped trigonal prism. Here we can see, as I told you, we find every coordination mode in this complex. We have the nitro and nitrito ones that are visible, and the bridging between every other potassium and the bridge between the transition metal and the potassium ion through the nitrogen and oxygen. One interesting thing is the chelatic potassium is always the one that doesn't have the water as a bridge molecule. Speaking of the of the imposter, we have here the potassium, two potassium ions being connected by the water molecule. For a brief introduction to the vibrational modes of the ligand, because we will get into the ER spectrum, the most common ones we can find are the bending mode, symmetrical mode, and asymmetrical mode, which you can see the values that they appear in. The rocking mode is it presents itself as a very low intensity band at 500, 600, and the vibrational mode for the metal nitrogen bond In some complexes, it's present at 400, 420, but it's very common that you can find it in 200. So we will not see it in most complexes. The same goes for the rotational mode. Okay, so moving on to the spectra, we have categorized in groups. As you can see, the spectra differs with the counter ion. So if we look at the simple family, we can see clear bands and not that much splitting. And the values here for the asymmetrical, symmetrical, and bending modes. And this is the one of the complexes that have a band for metal nitrogen mode. Okay. So the split and the shifting of the bands are caused by the counter ion through electrostatic interactions, which cause a shift and further splitting. Okay, so this is the DFT part where we did two sets of DFT calculations. The first calculation was done on the nitrate ion in order to see how the molecule behaves when it's not in a complex. So you can see clearly the bands and the mode that they vibrate in. So this helped us further assign bands to other complexes that we didn't find in the literature. We have the bending, the symmetrical and asymmetrical bands, and their respective vibrational modes. And here we have the ER spectra of a chunk of the structure that I showed you with the single crystal X-ray diffraction. And the bands are in accordance. 0 to 200 are the rotational and metal nitrogen vibrational mode. 400 is for the rocking. As you can see, it moves in the plane. This is the bending, which you can clearly see. And these ones, they calculated two modes for the symmetrical mode and one for the asymmetrical mode. And the order of the bands doesn't change, so we can safely assume that every other ER spectra is the same. And generally speaking, we can look at the values, but not so much. Moving on to the electronic spectra, one thing to keep in mind here is that because of the ligands and their interactions with the lattice, the geometry gets reduced from the octahedral geometry to a tetrahedral symmetry is reduced. This causes the Laporte rule to relax, making DD transitions a lot possible. This effect intensifies further with counter ions. The first complex we're going to look at is potassium hexanitrocobaltate, in which the cobalt is found in +3. It is found in low spin, and as you can see, the first one, the band here, the DD transitions are very weak because of his charge. The charge makes it that the splitting in orbitals is very larger. It basically acts, NO2 acts as a strong field ligand, even though it's a moderate one. And the transitions are not possible because the complex is low spin and there are spin forbidden transitions. In all the other complexes, we find the cobalt in high spin. And because of this, we now have some spin allowed transitions and further symmetry, further reducing of the symmetry, which makes the bands more intense. One thing I didn't mention is the charge transfer bands at 200 and 400, which they overlap with the first D transition, which makes the complexes colorful. Okay, here it's the same story, but the first transition in literature, and it is almost 10 DQ. So we can clearly, if we look at the band, we can clearly see the indirect effect the counter ions have on the split. So if we look at the strontium, for example, which is a bit off-red, it is lower than the complex with the first, with nothing at all, with only potassium. The counter ions modify the ligand field indirectly through electrostatic interactions. The further the trend was supposed to be, the further the charge, the bigger the charge, the more intense it gets. Lattice packing, how different counter ions affect the packing to their volumes. How the nitrate ion is coordinated, mainly to the oxygen atoms, and the polarization of the bond, again, with the charge of the counter ion. Here, the same goes, they're very similar in properties, but this one is different. And to note, because of the Young-Teller distortion, the charge transfer band interacts with the transition band. You can see in the 11 complex, which results in a red shift to bigger wavelengths and a broadening of the bands. A brief overview of the thermal analysis. We chose for this presentation to focus mainly on the first family of the complexes. The first step that we identified is loss of solvent. So the water gets evaporated, and nitro-nitrito rearrangement begins here and continues into step 2, which is the main decomposition. Now, there is a discussion to be had here, but the main thing is that as you can see, the mass loss is attributed to nitrogen monoxide and nitrogen dioxide that is liberated from the complex at these temperatures. Nitrate salts can also form, but the reason is split between complexes. Step 3 is the formation of these of the oxides of the transition metal, and because the analysis was done in air and not inert atmosphere, we don't have any we have the oxygen of we have the oxide of the transition metal forms, and the gases are okay. The main thing to note about the cobalt complex, in closing, is that redox processes take place. So we have a mixed oxide of cobalt 2 and cobalt 3 at the last step of the process. In closing, I would like to thank Dr. Badika, Lorenzi, and Barta for guiding me through my internship at the National Institute of Material Physics, and to my colleagues, which I spend most of my time in the lab with. Thank you very much.
Thank you.
Unfortunately, these smart magnetics usually suffer from low electricity and poor metabolic stability, and that limits their theoretical potential. On this mechanism, we synthesize and provide magnetics to see how it works when the process in conscious cells. Our strategy was to replace solvent exposed amino acid and put inside a draft of silicon to increase the electricity and volume. Also, we want to replace protein with the protein to change the efficiency and increase the efficiency. Our peptides were characterized with one-dimensional and two-dimensional and mark and carbon lines. Over time, we synthesized some of these essences. Hannah, are you okay? Yeah. It's okay. That's it. Yeah. No, very good. Um, yeah, okay, thank you for this disconnection. Do you think it's me? Yeah. Okay, just a second. Okay, do you see the presentation now? Yes, you can see it. Okay, so using solid phase peptide synthesis, Cortex mixes start with carbon with more protected amino with a recombined test. We use TN2 as activation reagent to activate carboxyl the amino acid. DPM, we use as a base to glutamate free amino group of the acid. Then it makes it more graphic and triggers the nucleophilic to carboxyl group of amino acid. To avoid amplification, we use HPT. After this step, we perform CATN to isolate any free amino present to avoid such chain elongation. After this step, we wash with specific solvents that you see on the slide. DMF, methanol, and after this step, we remove the smoke protecting group and using a team that removes specific acidic carbon disposition and it generates intermediate highly reactive depends that excess of hydrogen traps and removes from the solution. This component test how colorimetric reason test we use cursor and yellow solution indicates how carbon test as a reaction. We see blue carbon means this our test. The substituted was 29%. With substituted phenyl serine, in our solution this we have linear peptide. We use DSC activating reagent to activate hydroxychloroquine in this position. And the end is a base. And after this step, we perform collage with TFA fail. TFA has better hydrocarbon, and this is prevented using DSC unit from the solution. And we have our peptide out of the resin. To go more in details about our mechanism and intermolecular sensation, we start with hydroxyphenyl serine and declare that hydroxyphenyl. We have oxygen in this position that attack this methyl carbonate, and we obtain an anionic intermediate. At this step, base declium attacks nitrogen and makes it more nucleophilic. This step is solvent dependent, that's why we need a specific ratio of solvents. Is generated intermediate with the utilization of nitrogen and oxygen. After this step, activated nitrogen of our carbonyl group here, and we obtain our cellular scaffold. Next step is formation of stable intermediate without hydrogen. Next step is N-hydroxy-succinylmethyl group release the solution, and we obtain our peptide with oxygen ring. On this slide, we see all the structures that were synthesized with hydroxyproline, phenylserine, oxygen ring incorporated. Also, we synthesized inverse sequences and inverse sequences with oxygen ring. To obtain our 2D crossing spectrum, we perform the situation where we remove the peak of the water. Now we took the A7 structure and confirm that hydrogen 4 and hydrogen 5 present on our slide. In carbon NMR spectrum, we see the carbonyl group of the ring of our oxygen ring, and it's 154 ppm. By this vector, we confirm our structure and that the ring was incorporated. In conclusion, we modified our peptides at the binding and carbon positions, incorporated oxygen ring, and synthesized it through solid phase peptide synthesis. Then we characterized it with NMR spectroscopy. Future perspective. Also, we would like to mitigate isolation position. Then complete NMR analysis and zero variable temperature NMR to study quality combination. And also, we would like to do biological activities and say with our peptides. I will also thank you, my professor, supervisor, and collaborator for helping and guidance. Thank you for your attention.
Thank you very much. Are there any questions? If not, thank you very much for your presentation.
Thank you.
Bye. See you next time. Thank you very much. Thank you all for your presentations and involvement.